So what is the delay?
ജെയിംസ് നമുക്ക് സ്റ്റാർട്ട് ചെയ്താലോ?
ടീച്ചർ ഞാൻ മീറ്റിങ്ങിലാണ്, ഞാൻ അയച്ചു തരാം പിന്നീട്.
ഹലോ ജെയിംസ് സാറേ.
ഫ്രാൻസിസ് സാർ. തുടങ്ങാം. വൈശാഖ്
കേൾക്കാം സാറേ.
കേൾക്കാം. തുടങ്ങാം നമുക്ക്.
We request everyone to please turn off their audio for the better experience. Good morning, one and all. The struggle you are in today is developing the strength you needed for tomorrow. A huge welcome to one and all present. Let me introduce myself. Myself, Vaishak V, and I'm a student from the Department of Mathematics, Mother Teresa College. On this day, amidst this global pandemic, we have all got together for the first ever international conference held by the Department of Mathematics, Mother Teresa College. The international webinar on the uncelebrated genius, KSS Namboodiripad. As always, well begun is half done. We will begin the meeting with a silent prayer. Thank you, everyone. To keep things rolling, let me invite Dr. James Alexander, sir, the head of Mathematics Department, Mother Teresa College, for the welcome speech. Over to you, sir.
Respected Principal Dr. K. M. Francis, distinguished guest and a resource person, Dr. Asif Muhammad, respected teachers and dear students. It is my pleasant duty to welcome you all to this international webinar on KSS Namboodiripad, the uncelebrated genius. Dr. Namboodiripad has made fundamental contributions to the structure theory of regular semigroups. It is our conviction that webinar will offer us an opportunity to learn the basic mathematical work of Dr. Namboodiripad. Let me come to my duty. Our principal, Dr. K.M. Francis, is a source of inspiration. We welcome you most cordially. With great pleasure that I introduce Dr. Asif Muhammad to you. Dr. Asif took his PhD from University of Kerala in 2016 and he did his postdoctoral research in ISER Thiruvananthapuram. Then he proceeded to the prestigious Ural Federal University, Russia, and worked there as postdoctoral scientist. Currently, he is working as an assistant professor in mathematics, Prince Muhammad University, Saudi Arabia. Dear Dr. Asif, on behalf of our college and all the participants of this webinar, I extend to you a very warm welcome. We also welcome the teachers and students from various colleges, faculty members from other departments of the college, and our dear students to this webinar. I am extremely happy to welcome all the faculty members of the department, without whose sincere support and great initiative, this academic event would not be possible. Thank you all.
Thank you, sir. Now, let me invite Dr. K.M. Francis, sir, the principal of Mother Teresa College, who have always been the tower of strength in coordinating all our activities to address the gathering. Over to you, sir.
Good morning to all. Respected Chief Guest of the Day, Dr. Asif Muhammad, respected Head of the Department of Mathematics, dear faculty members, and my dear students and participants. First of all, I take this opportunity to congratulate the Head of the Department and the faculty members of the Department of Mathematics for organizing this international webinar. This is the second international webinar organizing by the college, and the first one organized by the Department of Chemistry yesterday. Mathematics department is the first department of the college to organize a webinar at the national and international level. I'm very happy to say that we are fortunate to get the great genius, Dr. Asif Muhammad, professor of the famous Prince Muhammad University, Saudi Arabia, as today's chief guest. It is very hard for me to remember his great profile, but one thing I can understand, that is, Dr. Asif is a model student and a person who respects teachers too much. That is why he selected this topic related to his beloved teacher, K.S.S. Namboodiripad, the uncelebrated genius. When we, in this context, we can say this webinar is a glowing tribute to a teacher by his students. This itself is the great message of this webinar. This webinar shows how should be the relation of students with their teachers. More than the person, the contribution of K.S.S. Namboodiripad to this branch of knowledge, mathematics, will of course be focused in this webinar, which will help all participants too much. I wish all success to this webinar. And I once again, on behalf of the college community, welcome today's chief guest, Dr. Asif Mohammed, to this great function. With your permission, I inaugurate this international seminar of Mother Teresa College, organized by the Department of Mathematics. Thank you. Thank you very much.
Thank you, sir, for your words of wisdom. Now, let me invite our resource person, Dr. Asif Mohammed PA, from Prince Mohammed University, Saudi Arabia, to take over the session. Over to you, sir.
All right. Thank you very much for the kind words and the invitation, first of all. I think I must mention this here at the outset, especially since we are talking about a real genius, we are mere mortals. So I think I have to clarify that. By the way, I think a couple of the mics are on. It will be nice if you can switch off all the mics so that there'll be no interruptions. I think James sir's mic is on. Yeah, I think that's better. So I think enough has been said about what I will be talking about. So it's better that I get started. Let me see how the presentation is loading. Can all of you see the presentation? Is it fine?
Yeah, okay.
Yeah, good. Fine. So, as it's been said, I'll be speaking about Namboodiripad and his work on mathematics. So, I think a lot of you know this. Namboodiripad was one of the the biggest contributors to, I would say, not just semi-groups, but even mathematics from our part of the world. But I've always felt that Namboodiripad has not received the due credit which he truly deserved. So that's why when James sir had asked me to give a talk, I thought like I should speak about Namboodiripad because, you know, especially the newer generation, a lot of people don't know. They don't even know the person, and at times, even if they know the person, they don't know what his work was. So I have tried to put up a collection of his work and some basic ideas of his work, and a little bit of history here and there to give you a feeling of the kind of impact Namboodiripad has made all throughout the world. I mean, he may not be a very popular person in Kerala or in Trivandrum per se, but he is quite popular in the semi-group circle. So I'll come to all these kind of aspects in the coming lecture. So it's basically a mixed bag. There is here and there. Sometimes things may go a bit tangential, but don't worry, I'll soon come back. All right. So I'll get started. I think that's it. So as I said, it's about Namboodiripad. This was Namboodiripad in his later days. So every story, it has to have a beginning, and I prefer to begin this story from not when he was born. So this is the mathematical story. So we'll be discussing the story since his mathematical part began. Okay. So now, first of all, the question arises: why do we need to talk about it? Okay. So it's as David McCullough said, how can we know who we are, where we are going, if we don't know anything about where we have come from and what we have been through? Or as Shashi Tharoor, I have had a lot of, I still have a lot of differences with Shashi Tharoor on a lot of issues, but I think I agree with him here. We need to know such kind of stories, because if you don't know where we have come from, you will never appreciate where you are going. And some historians say the past is like using a rear view mirror. So it's like a disclaimer. It's good to glance back and see how far you've come, but if you stare too long, you will miss what's right in front of you. So it's good to look at the history, it's good to look back, but we shouldn't get ourselves immersed in the history. Another disclaimer I forgot to mention, I should have told this in the previous slide. This will be somehow overlapping with my talks in Kochi and Chalakudi in December. So if I see some names, I think Kurian was there in Chalakudi. So there will be some overlap between this talk and the talks I have given there. So please bear with me. Anyways, so let's move on. Another disclaimer. So I'm putting up too many disclaimers. So this is not an appeal to make Kerala mathematics great again. Now you're actually going through that phase in history where everybody wants to make India great again, make America great again, make France great again, make Russia great again. So, somewhere or the other, it's very easy to sell this idea to the people that, okay, you've been great geniuses as a community once upon a time, and somehow something happened, and then everything just broke down. Now I am here to save you, to make everything great again. So, but this talk is not an appeal to that. This is a very simple talk with some simple motives, just to tell you about Namboodiripad, and it's more about giving the credit where it's due. All right, it's not just that there is a person and I've worked with him. I mean, I've worked in his area, and then I want to celebrate him. No, it's not like that. It's about saying that, okay, here is a person's work which has deserved much more but didn't get enough attention, at least not enough attention in the popular culture. Okay, he has got attention where it really mattered, I would say. Inside the semi-group community, Namboodiripad is still a rock star. So I mean, when I use the word rock star, I'm actually quoting Victoria Gould. I mean, she has used this word. So Namboodiripad is a rock star in the area of semi-groups, but people should know him better. At least people from mathematics background should know him better. So I think I've said enough about this. So Vaikam Muhammad Bashir in his book tells this. We have this habit of saying, okay, my grandfather had an elephant. Okay, let's not do that. So this is sufficient disclaimers regarding the talk. Now let's move on. So for me, the story starts in the 1950s from Maharaja's College. So this Maharaja's College, our Maharaja's College, the new Maharaja's College, which comes up in news every now and then. So Maharaja's College in Ernakulam. So a young man, his name was Subramanian Namburipad. Okay, Namburipad was his surname. His name was Subramanian for that matter. He graduated in mathematics from Maharaja's College. And he got placed as a mathematics lecturer at UC College. I think Kurian is here. Kurian is still in UC. Namburipad was there in UC College. But he found himself unhappy. He was not happy with his position in UC College. In fact, he has had several disagreements with faculty members, with students about the way things are being taught, how mathematics is being pursued. And all these are still relevant, even after 50 years, 70 years, everything is still very relevant. Anyways, he was not happy and he wanted to pursue mathematics research. Okay, he realized that he's not meant for teaching at some level, and he was in fact interested in Riemann hypothesis. Now, Riemann hypothesis is, if you know, it's a very, very big problem. It was like, if you ask even now what is one of the biggest problems in mathematics, we would say it's Riemann hypothesis. It's actually the Riemann problem is it's a part of the hypothesis. The hypothesis is that the Riemann zeta function has only zeros at the negative even numbers and at the complex numbers with real part equal to half. So this is the Riemann hypothesis. So this is a hypothesis, and it's considered to be one of the biggest problems. It was listed in Hilbert's list, or Hilbert's list of 23 unsolved problems. It's also a part of the Clay Mathematics Institute Millennium Prize problem. So this is a $1 million question. So I think just before the talk, we were talking about Richard Perelman. So Perelman is a person who has won the $1 million problem for his work on this Poincare conjecture. So this problem, the Riemann hypothesis, was a big problem. It's still a big problem. Okay, so this is actually the kind of levels of ambition, mathematical ambition that we should look up to. We are not talking about a small person. He is a person who was genuinely interested in Riemann hypothesis, and he was just not interested. He decided to take up his quest. He left his teaching position from UC College, and in fact he was associated with a couple of colleges. Another college, I think Kodamangala Engineering College or something. Anyways, he left this and he eventually came to Thiruvananthapuram. So he was born in Kochi and he came to Thiruvananthapuram in 1965. So there you had University of Kerala. Now University of Kerala, as you know it now, is not the University of Kerala what it was in the 60s. If you have heard this story, University of Kerala had a huge what you call reputation or history. Even the college had invited Albert Einstein to be the vice chancellor. So that's the kind of university, not of University College, of University of Kerala. So the department, the university in itself was a wonderful university, or a highly reputed university at that time. And if you try to relate it to what's happening now, it's virtually unrelatable. Now, it was a newly found department, a fresh, brand new department. And he joined the department. He decided, remember, he was working on Riemann hypothesis. I think I have not mentioned this. Riemann hypothesis is a problem in number theory. So you're dealing with numbers. Okay, so it's about analytical number theory. So Namburipad published a couple of papers regarding prime numbers, about distribution of prime numbers, and all. It's still available online. If you can put in a slightly non-trivial effort, you can see these papers on prime numbers done by Namburipad. It's published as a single author paper. Now he changed his supervisor, so his issues continued. This is the problem that happens with geniuses. They'll not be very comfortable in a lot of places with a lot of things. So he changed his supervisors twice before finally settling with a classical analyst, Professor Y. Sitharaman. So what exactly happened, or how he changed from prime numbers and why he changed his supervisors, we still don't know. He was clearly uncomfortable with several things. Now, why he settled with Sitharaman is something which we know. So his USP was that Professor Sitharaman was willing to let Namboodiripad pursue whatever he wanted. Okay, you do whatever you want, I'll support you. Okay, so that was the best quality which Namboodiripad saw in Professor Sitharaman. And the crucial thing that happened during this process, whatever we don't know, is that Namboodiripada's interest has also changed. He came with an interest in number theory. Now he was interested in systems which admit solutions to a random, not a random, first order or a linear equation, Ax is equal to b. So if you look at a simple equation, Ax is equal to b, you can ask the question, when do you have a solution? Now, this, in other words, you're looking at systems which kind of admit some kind of inverses for an element in it. So you look at some equation, X is equal to B. When will it have a solution? If you can find some kind of an inverse for A inverse, for A. So if you have A inverse, you left multiply it with A inverse. So you get A inverse Ax is equal to B, and somehow you bring this A inverse to the other side. So you have X is equal to A inverse B at some level. Okay, so this is how apparently Namboodiripad got interested in semigroups, and this affinity, or maybe his affinity towards this general cases, as I go through the talk, you'll see how general Namboodiripad was when he built his theories and stuff like that. General, the more general it becomes, the more difficult it is for people like us. Namboodiripad had a certain other, that's why I keep saying, Namboodiripad is of some other level. So for him, the semi-group of matrices it's too difficult. It's too difficult because it's too concrete. Whereas for us, a semi-group of matrices is something which we can associate, more relate to. But for him, an arbitrary semi-group or an arbitrary regular semi-group is something which he deals with. That's how he goes about his things. This change, and finally what it culminated in his interest in regular semi-groups. So regular semi-groups was what Namboodiripad worked on. I think one of the I think James mentioned this word regular semi-groups. So my aim of the talk is to give you what is a regular semi-group, what was Namboodiripad work in it, and why it is a genius. And I will just hint on why he's still celebrated. I won't be explicit. You may have to read between the lines. Anyway, so let's begin. So I'll be giving a crash course in semi-groups on maybe 2 slides or something like that, just for the beginners. I'm sure all of you are from mathematical background, so you know what is a semi-group because we all learn groups. And so semi-group is basically a non-empty set along with an associative binary operation. So in particular, a group is a semi-group. Okay, if you add inverses and identity, you get a group. So semi-group is basically a very simple general structure. Okay, but although a semi-group can be considered as a generalization of a group, observe that there are 5 non-isomorphic semi-groups of order 2. If you look at groups, can anybody tell me how many groups are there of order 2? I think everybody is here. By the way, 190 people, I'm giving such a talk to a big audience for the first time. Anyways, tell me how many groups are there of order 2? Anyone? You can tell it in the chat. You can tell it over mic. Please take part. Let's not make it a monologue. How many groups are there of order 2? How many groups are there of order 2? I like some of the students to answer this question. My question is, how many groups are there of order 2? Somebody please answer. Are you hearing me? Kurian answered. It's 1. Okay. Anyways, so there is 1 group of order 2, but there are 5 semi-groups of order 2. There is 1 group of order 3, but there are 24 semi-groups of order 3. There is how many groups of order 4? There is somebody else, somebody from the students. Can you tell me how many groups are there of order 4? How many groups of order 4? Students. Good. 2 groups of order 4. I hope these are students. Very good. But there are 188 semi-groups of order 4. Order 5, Again, one group, all prime numbers, you have just one group. So order 5, there is one group, there are almost 2000 semi-groups. Order 6, there are two groups, but you have almost 30,000 semi-groups. Order 7, 16 lakh semi-groups. Order 8, so on. So the list goes on like this. So we have a list till I think of 12 or 13. Beyond that, we don't have a list. So this is how diverse semi groups are. There are so many semi groups. So it's such a general structure that if you want to classify it, it's quite a daunting task. Okay, so this numbers tells that the semi groups do not resemble groups, although it may be seen as a general object or a generalization of groups. This complex structure makes semi-groups a very interesting object from our point of view. Now, let me give some classical examples of semi-groups. So, your set of natural numbers under addition is one of the basic examples of a semi-group. Another example, which is the prototype example in the case of semi-groups or even regular semi-groups, is the full transformation semi-group. So you look at you look at a set and you look at all the mappings on the set. Okay. In the case of a group, you look at one on two mappings. You look at bijections on a set that forms a group, the symmetric group. Here you look at the semi-group of all mappings, not just not just bijections. You look at all possible mappings, onto everything. Okay, and this forms a semi-group. Okay, and such a semi-group is known as a full transformation semi-group. So it's a semi-group of all transformations on the set X. Something which is more known to you, you take any ring or an algebra, you just look at its multiplicative part. This forms a semi-group. Another example which actually follows from full transformation is that you take a vector space and you take all linear transformations. You take all linear transformations on a vector space. This again forms a group, so a semi-group under function composition. In particular, your n by n matrices. So this is an example which I mentioned slightly earlier. So you take n by n matrices over a field. Now that's another semi-group under matrix multiplication. Now another very important semi-group is that of a symmetric inverse semi-group. Now here, this is actually something in between your symmetric group and your full transformation semi-group. In the case of symmetric group, you take only the bijections on a set. Okay, symmetric group. Everybody knows symmetric group, permutation group. All right. Now, your full transformation is the semi-group of all mappings. Now, suppose you restrict it to the semi-group of all 1-1 partial mappings. Okay, you want the mappings to be 1-1, and you also want it to be partial mappings. Okay, you consider all partial mappings also. Okay, there is a reason for this. Now this forms a very important kind of semi-group. It's called a symmetric inverse semi-group. I think I'll revisit this semi-group as I go through my slide. Another example of a semi-group, if you have done a little bit of order theory, is semi-lattice. If you take a lower semi-lattice, you can see that as a semi-group under its infimum. Again, this is a very important semi-group because a semi-lattice forms a what do you call it, skeletal system of a major class of semi-groups. Okay, so these are some examples of semi-groups. Some elementary ideas, I'll just quickly recall it for the benefit of what do you call it, totality of the talk. So an element is said to be an idempotent. I think everybody knows if E square is equal to E. Now there is a natural partial order on the set of idempotents of a given semi-group. So you take a semi-group, you can define a particular order among this idempotents. So this idempotence in the semi-group has some order. Now this one observation is actually the fundamental, or the I would say the foundation of Namboodiripat's work. So there is a partial order or a order among this set of idempotents. Okay, so there is a partial order, and in fact there is more to it when you go. I mean, on the whole of on the whole of set of idempotents, and you want to completely study the idempotents, you'll see that in the coming slides that there is something more to it. And I think it's Namburipart's genius what actually led to this discovery. So just like in the case of ring theory, you can talk of left ideals, right ideals, and a two-sided ideal in the case of semigroups. And finally, you have this principal left ideal generated by A, just like you have in the case of rings. And you have a particular equivalence relation called Green's L and R relations, defined by how this principal left and right ideals sort of partitions the elements of the semigroup. So the Green's relation on the semigroup is defined that two elements are L related if they generate the same principal left ideal. So and then that give rise to certain other equivalence relations. So if you are familiar with this, I think this will act as a brush up. Otherwise, I just want to give you a feel of the kind of theory which we do in semigroups. So you have this principal ideals, and this kind of classifies, or this kind of breaks up your semigroups into different equivalence classes, and that's the basic analysis which we do with semigroups. So I'll just give you a nice example of a picture which I always share with whenever I try to speak of semigroups to a general audience. So this is the example of a full transformation semigroup on 3 letters. Okay, so if I had a board, I could have written it, but unfortunately it's not working here so well. So so this part, the one on top, I hope my arrow is my cursor is visible to you. So this is actually the symmetric group on 3 letters. Okay, so you take the symmetric group. So 1, 2, 3 basically means 1 maps to 1, 2 maps to 2, 3 maps to 3. So this is the identity element of the symmetric group. So if you look at this particular box, this consists of 6 elements, precisely the symmetric group. Okay, which consists of 6 elements here. All right, so this is the bijections on the set 1, 2, 3. Then you have this middle D class. So this egg box diagram is called as a D class structure of a semigroup. So this 1, 2, 2 means 1 maps to 1, 2 maps to 2, 3 maps to 2. Okay, so this is an element. So you have this function 1 maps to 1, 2 maps to 2, 3 maps to 2. So that's a function. So that function is given here. You can see that this function is in fact an idempotent. If you multiply it with itself, you see that you will get back 1, 2, 2. So 1 maps to 2. What happens to 2? 2 maps to 2. So 1 maps to 2. So it's an idempotent. You can see this. You can verify it. Similarly, 1, 3, 3 is an idempotent. So this similarly you have this particular D class which consists of 6 into 3, 18 elements. And finally, you have this lower D class. Okay. So the Green's relation.
Excuse me, sir.
Yes.
So there is a comment on the chat box that we can see the presentation.
Oh, wonderful. So maybe I'll. Is it true for everyone?
Oh, no. I can see.
Yeah, then I think maybe Dia should just what do you call it? Relog in. You know, this happens every now and then with online presentations.
Thank you,
Okay.
sir. You can continue.
Yeah. So thanks for the message. I didn't get the notification for the message. Okay. Anyways, so so this is the full transformation semigroup on 3 letters. It's a very simple semigroup. I give it because I, you know, after a full talk on semigroups, if you don't know full transformation semigroup, or when it's given to you, you don't realize it, then I think it's bad. So that's why I give it. And what do you mean? How does the Green's relation work in this semigroup? It simplifies to the fact that 2 elements are L related if they are having the same image. So you see that these elements on the same column will have the same image. So what's the image of this function? This function is 1 maps to 1, 2 maps to 2, 3 maps to 2. So the image is 1, 2. Similarly here, the image is 1, 2, 1, 2, 1, 2, 1, 2. So this elements in this particular column are basically elements which have the same image. Okay, so these are functions which have the same image, and we can show without much difficulty that 2 elements are L related if they are having the same image. Okay, so elements in the same column are L related, and elements in the same row are R related, and the characterizing property is that they induce the same partition on the set 1, 2, 3. So I think I'm not spending more time on this. Let's move on to what we want to discuss. We want to discuss about Namboodiripad and Namboodiripad work. So this is a classical example of a semigroup. So I think I have to be a bit more faster. So let's move on. So what did Namboodiripad do? Namboodiripad basically worked on a fundamental theorem for semigroups. Okay, so that's what he worked on. He wanted to build a fundamental theorem for semigroups. Now, what does a fundamental theorem means? It's a structure theory. Structure theory means you are looking at an object and you want to explain it using better known, simpler objects. Okay. So for example, you have this fundamental theorem for abelian groups. Any finite abelian group is isomorphic to a direct product of cyclic groups of prime power order. So this is a classical explanation of structure theorem. So you're telling that you give me any finite abelian group, I will give you its decomposition or how it's built up. Okay, so that's how a structure theorem works. Basically, Namboodiripad was trying to build a fundamental theorem for semigroups. Now that's a big question, but semigroups are rather general objects. So the building blocks would still be general. It will be something like sets, semilattices, groups, groupoids, categories, etc. And still you will have to look for some special classes. You cannot just give an arbitrary semigroup structure theorem. That's a very, very what do you call ambitious project, just like say Riemann hypothesis to do structure theory for arbitrary semigroups. So one of the first classes studied was inverse semigroups. Now inverse semigroups is basically a class of semigroups which is very close to your groups, in the sense that every element has a unique inverse. Now this inverse is not your group inverse. This is a special kind of inverse. It's called a generalized inverse. So this inverse has the property that x prime x is equal to x. Okay, so this and this additional condition x prime is equal to x prime is satisfied, then you say it's a generalized inverse. Now just as every group can be seen as a permutation group, every inverse semigroup can be seen as a symmetric inverse semigroup. Symmetric inverse semigroup is the semigroup of all partial 1-1 maps. I just introduced you when I introduced this thing, the examples. Now in inverse semigroups, it's a very big class. It's one of the best classes studied, and they encode the notion of partial symmetry, just like groups encode complete symmetry. And its origins can be traced back to the late 19th century. And one of the first structure theorems in semigroups was in 1970, when Munn described the structure of fundamental inverse semigroup. Now, fundamental basically means you have a structure. You are able to give the structure of the semigroup. Okay, so I'm being a bit quick here because I want to move on to the crux of the topic. Now, Munn showed you can construct an fundamental inverse semigroup from its semi-lattice of idempotence. So you take a inverse semigroup, its idempotence form a semi-lattice, and using that semi-lattice you can somehow give the structure of the fundamental inverse. Now another equally promising approach was started with Shine in 1965. Now this is how semigroups work. Somebody from the west will do something, somebody from the eastern bloc will do it. This is known as the mathematics behind the curtain. Semigroups grew up during the Cold War era. The history of the semigroups, there is a book on it. It's called The Mathematics Behind the Iron Curtain. So you do something there, somebody will do something from the eastern bloc also. So Shine in 1965 introduced a method to study arbitrary semigroups. He connected ideas of Wagner. Wagner was again a Russian mathematician. Ehresmann was a French mathematician. And this can be seen the first instance when small categories were used in semigroup structure theory. Now, I'll just tell you what is a small category. A small category basically means you get a set of objects, and for each pair of objects, you have a set of morphisms. And these morphisms are nice in the sense that they have associativity and there is existence of identity. So actually this associativity property is what makes your small category a crucial or a good candidate for to make it the building block of a structure theory for semi-groups, because you have associativity coming from the category part. So this category, you can see that in every morphism is invertible. It's called a groupoid. The groupoid with a single object is a group. So a groupoid basically is a generalization of the notion of a group. Okay. So I think I'm running short of time. Anyways, so Shine's approach basically relied on the fact that a groupoid can be naturally associated with an inverse semi-group. So this there is a natural way of associating a groupoid with an inverse semi-group. With a group, yeah. So you take any element, you can see that as a morphism or an arrow from your element x inverse to x inverse x, and all this idempotence will act as the identity element morphisms, and you can compose them in a very natural way, and this forms a category. Okay, so you take an inverse semi-group, you can construct a category which is in fact a groupoid, in the sense that you have every morphism has a inverse morphism also, and you given an inverse semigroup, you have an associated groupoid, and this idempotence will form a semilattice under the natural partial order, which I just briefly told you at the beginning of the talk. And the vertex set is a semilattice, and the morphisms are very nice in the sense that each arrow can be restricted or co-restricted. These are technical terms. Now, basically means you have a groupoid which has some additional structure. And conversely, you take an axiomatically defined inductive groupoid. So such a groupoid is called an inductive groupoid in the sense that there is a inductive structure underlying it. And conversely, given an inductive groupoid, you can associate a unique inverse semigroup. Now, this theorem, it was done by a lot of people from various parts of the world, as the name suggests, Ehresmann, Shine, Nambu-Ripard theorem. So this was actually, the name was given by Mark Lawson in his biblical book, the inverse semigroup theory of partial symmetry. So now Mark Lawson gave this name Ehresmann, Shine, Nambu-Ripard because of their contributions coming from different directions. Now observe that Ehresmann and Shine had worked on inverse semigroups, but Nambu-Ripard has never explicitly worked on inverse semigroups. Why? But still he was credited with this name for this inverse semigroup. Why? Because of his work on regular semigroups. Now, what is regular? So finally, I come to regular semigroups. A semigroup is said to be von Neumann regular if for every element there is a generalized inverse. Okay, so, and this inverse need not be unique, as in the case of inverse semigroups. Okay, so every inverse semigroup is regular, every group is regular, but not the other way around. So regular semigroup can be seen as a very natural generalization of groups and inverse semigroups. It arose from von Neumann's groundbreaking work on continuous geometry and his work on regular rings. Full transformation semigroup, linear transformation semigroup, matrices semigroup, inverse semigroups, all these are examples of regular semigroups. So all the classes we have mentioned so far are in fact regular semigroups. So regular semigroups forms a very major class of semigroups, and they are a very natural study. So it was tempting to generalize Munn's and Shine's result to regular semigroups, but one had a very quite daunting task in hand. You have to understand the idempotent structure of such regular semigroups. Now, two distinct approaches to this was established in the 70s. I'll start with the one which I'll come back later on. It's the indirect approach, where you don't directly deal with the idempotence, but you somehow use the ideal structure and you try to or you bypass this idempotent problem. What is the idempotent? You kind of bypass it, and this was initiated by Tom Hall, an Australian, and Gruyev, who was in I think Tulane later. He was in the US. So, but the second approach, it was more closer to what's Munn's original one. So it had a daunting task in hand. Now this came from a completely isolated source in India, and it had explored the idempotent structure of a semigroup. So you start from the semigroup. What is its idempotent structure? Nambu-Ripard gave the answer. So this was how Nambu-Ripard literally burst into the scene of semigroup theory out of nowhere. He had no library facilities. This was in the 1960s. No limited access to existing in literature, no internet, effectively no guide. He had nobody to discuss semigroups, no communication facilities. You had to write letters from here to wherever, US, UK. You have to write letters, wait for the letters to come back. It would take months, years at times, but Namboodiripad solved his problem. Now he literally solved his problem out of nowhere, and I think this is why Namboodiripad was a genius. He solved a virtually impossible problem. As John Fountain is a big, okay, I'll say John Fountain's tribute just appeared in Semigroup Forum last issue. So he's one of the what you call building blocks of semigroups, I would say. So John Fountain says that Namboodiripad solved this problem because he did not know that it was impossible. Nobody told him that this was impossible, so he solved it. Okay. Now Mohan Pucha is another American mathematician who's worked on biordered set structure on a group theoretic framework. So he says that the axioms are quite complicated. So Namboodiripad, what he did is he gave some axioms. He said that, okay, a set satisfying this is properties is called the biordered set, and this is the structure of the idempotence of a semigroup. Okay. So Mohan Pucha exclaims that it's rather surprising that such a finite axiomatization is even possible. Now, Mikin and Rajan in their tribute says that was done under virtual isolation under modest circumstances, and all this basically tells this story of Namboodiripad is the semigroup analog of what Ramanujan did in number theory. Now, to be precise, Namboodiripad axiomatized the structure of a regular semigroup as a regular biordered set. Later in 1986, Eastdown proved that the biordered set axioms were complete. Okay, so these are the axioms of the biordered set. I just show you a glimpse of these axioms just to give you a feel how difficult it is. So you have set as defined here. So it's a set with a partial binary operation satisfying these axioms B1, B2, B3, B4, B5, and finally there is another additional axiom, so I haven't named it. This is called the regular axiom. So he called the biordered set regular if this set satisfies these 13 axioms. Okay, so this is what Namboodiripad did in his PhD thesis, and he called them regular systems, and he extended Shine's result to regular semigroup. Now there is a historical angle to it. Simultaneously, another Australian devised an exciting new approach called structure mappings to study inverse semigroups. He sent his work to Clifford, who was one of the founding fathers of semigroups. And Clifford tells this Australian guy that an unknown Indian guy has apparently developed this idea, but in a very general class. Now, this Australian gets deeply depressed, but he wrote letters to India, and he decides to visit this man to see whether he is actually, a real person. And he finally comes to India in 1978, and this was John Meakin's 1978 visit to Kerala. So this is actually a picture taken from 1978. John Meakin has been a big inspiration for all of us in the semigroup community here. He has been a regular visitor here. He even visited us in 2019 during the conference. This is a picture from 1978, John Meakin's visit. Some other pictures I have, these are some familiar faces. This is Krishnan sir, if you know him. This is Rajan sir, and this is Veeramani sir. So all this was part of Namboodiripad research group in 1978. So this is what the picture was in 1978. Now I'll slowly tell about what happened afterwards. Now Namboodiripad thesis was finally published as the memoirs in 1979 with the help of Clifford. So Namboodiripad made some additional structures, and in the memoirs he showed a categorical equivalence between regular semigroups and inductive groupoids. So there is a categorical equivalence between semigroups and groupoids. Now this kind of equivalence was unknown till that time in the area of semigroups, and that is why when you specialize this to inverse semigroups, you will get the so-called ESN, Ehresmann-Shine Namboodiripad theorem, for your inverse semigroups. And it's in fact this contribution which makes Namboodiripad name appear here, this category equivalence. Now further Namboodiripad, so I'll briefly tell you the other results from the memoirs. He generalized it to Munn's result for inverse semigroups. He gave it as a specialization of Munn's and Greeley's work. He studied free regular idempotent semigroups, I think I don't have time, so I'll not spend much time on this. And he gave some characterization. Now, what happened was, so I think I have to mention this in spite of the lack of time. He sent these memos to TIFR, and he didn't get, it was not well received from TIFR, and that sort of made him at cross with the so-called mainstream mathematical community in India, and that actually sort of had some impact on what happened in his life afterwards. Let's move on. Let's not delve into this now, especially because of short of time. I'll just give you a feeling of what all is the impact of Namburipad's work. Namburipad's work was generalized heavily by the York School in UK, by Armstrong, Gould and Wang, Gould and Yang, and so on. In another direction, Xiaofeng Wang, Mark Lawson, Christopher Hollings, Ben Steinberg, Gowan Chen, Itamar Steen, all these people had worked on generalizations of ESN, which heavily relies on Namburipad's work. So this can be seen as an impact of Namburipad's work and how Namburipad has affected the world of semi-group theory, at least. And there is one biggest problem associated with your Bided set is how it's maximal subgroups behave. This has received wide attention from early 80s till 2000, and then it was having a silent gap from 2002 to 2009. When 2009, Britton and Margolis and John Meakin proved that their conjecture that these groups are free is wrong, and this led to another flurry of literature. Gray, Nick Rushkock, Victoria Gould, Dundon Yang, Igor Dolinga, Nick Rushkock, Eastdown, Mark Sapir, Mikhail Volkov, Robert Gray, and so many people, so many others, O'Brien, all these people worked on this problem. To tell you, to get a feeling of the quality of the work. So in this 2009 work by Dolinga, Gould and Young, it was published in Advances in Mathematics. So Advances in Mathematics is like one of the top journals in mathematics. So that's the kind of impact Namburipad's work has had on semi-groups or in mathematics. Now, another last piece, which I like to finish it off in 3 words. I think it would be unfair to finish off a talk of Namburipad without talking about cross connections. So this is basically a work initiated by Hall and Grillet based on building the fundamental image of a regular semigroup. Namburipad had an impossible related idea in this, to actually provide a structure theorem for semigroups using small categories. So for that, he pursued this cross connection construction. He constructed what's called as a normal category and a cross connection which describes the structure of this regular semigroups, and he showed that there is a correspondence between regular semigroups and cross-connected normal categories, and he proved a categorical equivalence. So this initial manuscript was written in his late 80s during one of Namburipad's visit to US, and on return, Namburipad carried another valuable thing with him in a set of 14 floppy disks. It's LaTeX. This presentation is made on LaTeX. I'm sure a lot of people will be using LaTeX in Kerala right now, but Namburipad brought it to Kerala, or in fact, I think for the first time to even India. So this was in late 80s. Namburipad brought LaTeX. He was a big proponent of LaTeX and free software users and free publications. So he wanted his publications to be free, and that's why he decided to put his publications under Center for Mathematics Sciences, and he had a publication number 15, and then this was again published in 1995. A lot of personal tragedies occurred to Namburipad in the early 90s, and that's had an impact on his work. And his academic interest sort of waned by the year he retired. He was still interested, but the cross connection theory was in a limbo up until recently. Some classes had been studied, and categorical equivalence was proved by me and Professor Volkov in 2020. The result is not yet published. So this is some of the recent work on cross-connection theory. Now, there are a lot of future directions. I think I'm running short of time. I think I must wind up because it's almost 11:29. So one major advantage of cross connections is that, as I mentioned, it actually goes into the heart of the structure of an arbitrary semigroup, that it's composed of two components, left and right. So the philosophically, it's very natural that you want to generalize your, if you want to generalize the theory for arbitrary semigroups, you want to look at cross connections, and you have to look at two categories, not one. And this led to what was Namburipad's favorite open problem. So he proved that you can construct two set-based categories from the principal left and right ideals, and he conjectured, so the remaining part is the conjecture of Namburipad, that you can connect it using a cross connections, and thus you can give a structure theory for arbitrary semigroups. So this is an open problem for those who are interested in Namburipad's work. If you solve this, this is like one of the benchmark problems. You will be known in semigroups if you can solve this or complete this. So some other connections, I'll just wind up with some connections beyond the usual semigroup things. Mohan Pucha studied opposite parabolical subgroups. So it's not that Namburipad restricted him to semigroups. He went beyond it. He tried to connect it with group theory. Professor Krishnan studied Fredholm operators. So you can have a study of Fredholm operators using Namburipad's approach. Krishnachandran studied topology and geometry associated with semigroups from Namburipad's approach. James Sahar is here. He studied von Neumann's construction of regular rings from Namburipad's perspective. Namburipad himself was interested in von Neumann algebras, and that was one of his favorite problems during John Meekin's 2014 Fulbright visit. I would say this was the last occasions when Namburipad was really in his hole. He was active. I was lucky to have been a part of this visit. So this takes the theory back to its roots. So it's a long time, almost 35, 40 years. John Meekin's association with Kerala and their mutual collaborations was something which we should look up to. He's still a very big inspiration for all of us, good wisher. I just got a mail from him right before I went logged into the talk. So we just completed a paper on Namburipad's work, which will be appearing in the along with Rajan sir, which will be appearing in the proceedings of Kochi conference. And this was so this sort of completes the circle. Von Neumann algebras to regular rings to semigroups, back to von Neumann algebras. Similarly, Maharaja's College, back to Maharaja's College. So this was, I think, the last occasion where Namburipad was really, as a whole, he was quite actively involved. This was a talk given by John Meekin as a part of their lecture series to celebrate the alumni of Maharaja's College. The photos were done by Mrs. Glory Meekin. All the photos, even the old ones, are by Glory Meekin. I think we'll stop here. Namburipad passed away in January this year. It was at some level expected. He was suffering from hydrocephalus, and he was in his hole in the last 2-3 years, I must admit. He has been a true genius, a true inspiration, but as I mentioned, due to some unfortunate circumstances and some unfortunate events, he hasn't received the kind of celebration which he truly deserved. And so this talk is basically a tribute to his mathematical genius and his works. And I hope that it's been a big audience here. I've never spoken to such a big audience. I hope I may have inspired or at least given a feel of what Namburipad did and the kind of impact he has had all over the globe on semigroups and beyond semigroups. So I think I'll stop here. I think I've taken already 3 minutes more. Thank you. If you have any questions, I'll be happy to take it.
Thank you, sir, for the insightful session. It was very much interesting and informative. Now we move on to the interactive session. Participants who have any questions to the resource person can ask their question in the comment box.
Anything? Nothing. That's it.
So there are no questions yet. We
Okay,
hope
everything
that
is
everyone.
clear.
So moving on,
Yeah.
now I invite Anius Norbert of S3 Mathematics for the vote of thanks.
Honorable Chief Guest, Dr. Asif Muhammad Sir, our most valued principal, Dr. K.M. Francis Sir, respected head of the department, Dr. James Alexander Sir, teachers, and my dear friends. It's my privilege to have been asked to propose an vote of thanks on this occasion. I acknowledge the contributions of those who worked really hard to make this event a grand success. I must mention our deep sense of appreciation to Dr. Asif Muhammad Sir, who delivered an excellent speech and spared his valuable time to grace this occasion. Indeed, you have put your best effort to make this event unforgettable. We are all inspired by your great words, sir. I must thank our respected principal, Dr. K.M. Francis Sir, who stands as a pillar behind every success of our college. On behalf of everyone, I thank you for your presence and your support. I would also thank our beloved head of the department, Dr. James Alexander Sir, for his guidance and his logistic support. Thank you so much, sir. I am happy to express a word of thanks to our teachers who are the coordinates of this event. Finally, I thank all the delegates who have turned up in such great numbers, not only from our department, rather also from other departments and other institutions. Thank you all for your cooperation. Once again, I thank one and all who is present here. Thank you.
Thank you, Annie. Thus, we come to the end of the first international webinar organized by the Department of Mathematics, Mother Teresa College. Participants, please make sure that you fill the feedback form which is provided in the chat box. Thank you everyone for your cooperation in making this webinar a success. Thank you and have a nice day.
Thank you.
That's it, sir. Thank you very much.
Thank you very much. Thanks for the invitation.
Thank you.
I think I have outboard you at least. All right. Thank you.
Thank you. Thank you.
കുര്യനോടുണ്ടോ?
ഉണ്ട് ഉണ്ട് ഉണ്ട്.
ഞാൻ ഫോൺ വിളിക്കാം.
ഓക്കെ.
Yeah. Thank you, sir.
Thank you.
Thank you.